All right, AP students, welcome to your final lecture in Unit 5. We're going to be talking about deeper about the implications of being a multi-step reaction, what it means to break down a reaction's mechanism into multiple phases or checkpoints that allow us to, one, understand most likely how the reaction that actually most accurately occurs. Oh my goodness, most accurately occurs. But two, also understand how a reaction can be simplified in a way that's more effective than trying to do it all in one round. So, since most reactions occur in two or more steps, due to the fact that it's easier to break down the process than do it all in one shot, because of the needed energy required to break the bonds, as well as the orientation that it would require to align two or more. Okay. What we see is a multi-step process. So remember originally, okay, we were talking about an energy diagram and how this hump up here is known as the transition state or the activated complex, right? And how we start with a given amount of potential energy in the reactants stored in the chemical bonds, the difference in height between the reactants and the activated complex potential energy is known as the activation energy, the minimum amount of energy that the particles must collide at in order to actually initiate the bond breaking and new bond forming. And then, of course, our products are at the other end. Okay, so that's what we've simply done is introduce. And then we even introduced, adding a catalyst. And adding a catalyst creates a new pathway, right, to complete the reaction, often lowering the activation energy. And I'm just going to use this symbol for activation energy. But what we haven't really talked about is where we see evidence of this multi-step process. Like we can logically argue, like, yeah, that makes sense. Like breaking the reaction down, and instead of having three things, collide at once, I can have two things collide, and then the intermediate of that collide with the other one, right? Like you can kind of rationalize it, but like where is kind of the evidence for this? Well, the evidence for this actually lies in when we throw in a catalyst. Oftentimes, the way that a catalyst speeds up reaction and changes the activation energy is by creating a new pathway that involves multiple steps. So oftentimes the catalyst is actually also not only the pathway to a faster and more efficient, higher probability collision reaction, but also a pathway to generating and understanding and confirming that there is multi-step mechanisms that happen sequentially in order to produce the overall reaction itself. Okay, so here's an example of what happens when we add a catalyst to the new reaction. Now what we have is we almost have, right, phase 1, phase 2, and phase 3 that break down the overall reaction. And we still end up with the same reactants and products, right? But what happens is the pathway changes. Now, initially you're like, whoa, 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 that looks more complicated. But notice all of the relative activation energy levels for the respective, what we call elementary reactions, right? All of the relative activation energies are significantly lower, okay, than the original. The original was up here. We are now down here. So we have overall decreased the activation energy value. Okay. So I don't know if any of you guys have been like camping or anything, but I remember going on a backpacking trip, and what we would do is instead of like climbing a mountain straight up, which you would think would be the fastest, most direct way, it's awful, right? Your legs go jello, your back hurts. I was carrying a 50-pound backpack. It was terrible. It was taller than me. It was too much. What we would do is we'd do switchbacks, right? Taking the circuitous pathway of going like this at an angle up the mountain. It ended up being more effective. Our success rate of us achieving, each of us in the team achieving the climb, I guess, was much higher than if we would just went straight up. Like I would have been the first to go 100%. I would have just slid down that mountain. Okay. So kind of the same idea. So when we break down a reaction into multiple steps, right? Multiple elementary steps, which I've introduced in the last lecture, there are 3 elementary steps now. Okay. When we do this, there's always one elementary step that we say is the rate determining step, the slowest step that overall determines how fast the reaction is. So kind of like the concept in stoichiometry of the limiting reagent. Now we're talking about, well, what's the limiting step? What's the limiting checkpoint? What's the limiting elementary reaction? And we just use a different name. We call it the rate determining step. So the rate determining step, or also known as RDS, okay, is the slowest elementary step in a reaction mechanism that determines the rate of reaction. And I should say the overall rate of reaction, right? The overall rate of reaction. So how do we identify what is the rate determining step? Well, the most obvious identification is that it has the highest activation energy. Okay. Second, you can often notice that there usually involves a more complex geometric collision. Okay, so like the bigger the molecule, the more complex it gets to hit it exactly in the right spot to break it where you want to break it so that the new bonds form where you want them to form. More complex geometric collision. Also, when you just simply have a low reactant concentration, the step before you doesn't produce the intermediate fast enough, which is now your new reactant. So you're kind of waiting. You're waiting to get the relative reactants that you need to complete this next step, right? Low reactant concentration. And then finally, if you have anything such as a term molecular, a 3-particle collision required, okay, you're definitely the elementary step, like 100% you're the slowest thing there. So in our reaction, we would say that the rate determining step would be the second one right here, highest activation energy from the relative products, right? So where the relative products start, okay, the activation energy is this amount, okay? Oh, and I see I actually made a mistake. I drew these activation energy arrows a little wide or a little long. It goes, actually, let's see. That goes from there, the relative reactant. This goes from here to here, the relative reactant. And this goes from here to here, the relative reactant. Okay, so we can see that the second step is going to be the largest. Okay. I don't really have confidence if this is a more complex geometric collision. I don't really know if I have low reactant concentration. I don't really know if I have term molecular, but I do know that I definitely have the highest activation energy. Therefore, we would say the second step in our reaction is the rate determining step. So, early in the morning. So, what we say is that the rate determining step, the RDS, activation energy, for the most part, is what determines or dictates the rate at which a reaction can occur. And of course, how do you calculate activation energy? Activation energy is equal to the potential energy of the activated complex minus the potential energy of your reactants. Well, your relative reactants, right? Because if you're doing multiple steps, right? So, here's a practice problem. Go ahead and identify which one is the intermediate. And then you're going to share in class. Make sure you have an explanation. Okay. And I'd also like you to identify how many steps are involved. So tell me the number of elementary steps and tell me which one is the RDS and how did you know? Okay. So that's what you're going to do. And then you're going to share in class and we're going to move on. So how do we determine the rate law for a rate determining step? Okay, reaction. Well, first and foremost, what you should notice is, let me collect my thoughts and make sure I'm clear on this. When we look at a reaction, so we're actually going to use the reaction above as our example, okay? When you look at a reaction and you notice that the rate determining step is not the first reaction, okay? So let's say for here, we have the rate determining step being on our second elementary reaction. The reaction between HCOOH2 plus and H2O plus HCO plus, okay? What we need to understand is that we need to identify one, the rate determining step, the overall reaction, and then determine the rate law based on the RDS. Okay, I don't think I explained that very clearly. Let's just start doing the problem. So I'm going to color code and I'm going to break this reaction down into the 3 steps. Okay, the first steps are this section. The next step is this transformation. And then the final step is this transformation. Okay, so let's break this down. So the first elementary step, we would write that H plus reacts with HCOOH and we get HCOOH2 plus. The next step in the reaction is that our previous product now becomes our reactant. So HCOOH2 plus reacts to produce H2O. It actually breaks down and HCO plus. And then our reactant was the product for the previous elementary step. So we have HCO plus goes to CO and H plus. Okay, and that would be our elementary steps. Okay, so what you notice is immediately we have a lot of intermediates that get canceled out when we do the overall. So our H pluses cancel. We have one on the reactant side. We have one on the product. Our HCOOH2 plus cancels out as an intermediate. We have one on the reactant. We have one on the product. And our HCO plus cancels out. One on the reactant, one on the product between our 3-step mechanism. And we get that our overall reaction is HCOOH plus H2O and CO, okay? So that's our overall reaction. Now, what were our intermediates, okay? Well, our intermediates were three of them. H plus, HCOOH2 plus, and HCO. Okay. And actually, I just made the common mistake. Our intermediate does not include H plus. Actually, H plus is what we call as our catalyst because it is consumed and then regenerated. It is consumed and then regenerated at the end. But our intermediates, okay, were HCOOH2 plus and HCO plus because they were produced but then consumed. Okay, so that's kind of the overall. And the question is, now that we kind of broken that down, we've identified the mechanism, we've identified the key roles that each particle plays, is how do we now do the rate law? Well, first and foremost, you need to determine the rate determining step. So step one, okay, determine the rate determining step. And for us, okay, the rate determining step is the second step. Okay. So that's kind of a problem. It's kind of like makes it complicated because if your rate determining step is the first step, it's super easy, right? When your rate determining step is the first step, okay, it's really easy because you can just write your rate law. Based on the first step reactants. Okay, but for us, we have something a little bit more complicated. We have the second step because we have a super complicated, right here. We have a super complicated intermediate, a more complex, okay? So, that's interesting. What would be the next step once we determine the rate determining step? And for us, this happens to not be the first step, okay? Well, when we have the rate determining step not be the first step, what we have to do now is we have to assume all other steps are in equilibrium. Equilibrium means that the rate of the forward reaction is equal to the rate of the backwards reaction. Okay? And then what we do is we use the coefficients okay? Or another way of putting it is the molecularity of reactants in the rate determining step as a guide for the reaction overall rate law and reaction order. So this sounds really complicated. I promise you, it will make sense. Let's just work through an official problem, okay? So one second, I'm gonna actually switch out pens because my pen's dying. Okay, I switched my pens out. So let's look at this problem. What we have here is we have a reaction between nitrogen monoxide and chlorine gas, and it goes through this two-step mechanism. And we notice immediately that they tell us that our slow reaction, our rate determining step is the second step. So that means that we're going to have to go through the process described above, and we can't just simplify it to the first reaction. So quickly for reference, okay, let's pretend if the RDS was the first reaction, okay, if the RDS was the first reaction, what we could do is we could just say that the concentration of NO, right, the rate of the reaction is best estimated through the reaction rate of the first elementary step. And that would be the concentration of NO to the power of 1 times the concentration of Cl2 to the power of 1, okay, times K rate law, okay, and that would be it. That would be all that we needed. If the RDS was the first reaction, it's so simple because we don't have any intermediates to worry about. We don't have anything before us to worry about. All we're doing is we're treating the entire reaction rate as if it is completely and wholly defined by the first elementary step, right? And let me put that in words for you. Oh my goodness. Why wouldn't it let me click on the black? There it is. Here we are treating the overall reaction rate as if it is wholly defined by the rate of reaction for the first elementary step. Elementary step. Okay. If the RDS was the first reaction, it's super simple. That's why I'm not spending very much time on it. Okay. But alas, that is not our case, right? Our case is the exact opposite. Our RDS, why is this not working for me? Our RDS, oh my God. I made a mistake, is the second step. So we need to rethink how we're going to do this. Like me, I'm trying to rethink how to make this smaller and why this pen hates me. Hold on. Hold on. I think I got it. Nope. The first elementary reaction step. Okay, sorry guys. Consider this your mental break as I struggle to figure this out. This pen really does hate me. Oh, okay, got it. So, but we don't have that. So let me make a little sad face. Sad. We don't have it this easy. So for when the RDS is the second or third or just not first, okay, what we do is we write the rate law, okay, and we write like what it would be theoretically. So we would do step 1, write the rate law. We would say that the rate is equal, I'm going to put K prime so that we know that it's going to be important that we notify it as K prime. It's not the first step rate, right? Because every K is with respect to each individual reaction step, okay, or individual reaction. So I'm going to call it K prime because it's the second step, okay? It's the rate constant for the second step. And to the times the concentration of NoCl2, okay, and the concentration of NO. Now, remember for elementary steps, we can use molecularity or like the stoichiometric molar ratios to be the reactant orders for the respective reactants. Because what we've done is we've simplified the mechanism so that we can actually trust that the coefficients indicate something about the relationship between the concentration of the reactants and the rate itself. Okay, so that's kind of what we write. And here's the thing, we need to recognize that NoCl2 is totally an intermediate, right? This is 100% an intermediate. So that's going to be a problem for writing out the final rate law for the overall reaction based on this rate determining step. So what we're going to do is we're going to do a substitution process. And the substitution process involves a concept that you will learn in much more detail in Unit 7. But for right now, I'm just going to introduce the math to you. And when Unit 7 comes along, it will all make sense. So we're going to use substitution, okay, and using what we call the KEQ, or the equilibrium expression. And the equilibrium expression equals the products, the concentration of products over the reactants. Over the reactants raised to their respective coefficient. Raised to their respective coefficients. Okay. So whatever the coefficient is in front of your reactant, you raise that. Okay. And so for us, then our KEQ for this reaction, our equilibrium constant, because remember, when we were talking about when we don't have the rate determining step as the first step, we have to assume that all other reaction steps are in equilibrium. So we're assuming consistent, pretty much non-important rates for them. Like their rates become insignificant to us. So all we need to assume is that they're still reacting. They're reacting at a rate that is reasonable and not affecting dramatically the overall reaction rate. So that's why we're able to use KEQ, because here we are assuming all other steps are in equilibrium. The rate of the forward is equal to the rate of the backwards. The rate of producing is equal to the rate of undoing. Okay, so there's a constant kind of concentration, basically, for your intermediate reactant and your consuming of the product that you produce, which could itself be another intermediate. Okay, so when we write this, we get that KEQ is equal to the concentration of NoCl2 all over the concentration of NO and Cl2. And since they have a coefficient of 1 in front of them, all of them do, we just leave it at that. There's no power raised, really, except raised to the power of 1. And so what we do then is we notice that we have a common, right? We have a common molecule here. So what we're going to do is we're going to rearrange this equation to solve for, well, what would the concentration of NoCl2 equal according to the KEQ equilibrium expression? Okay, so that we can hopefully actually get rid of the concentration of the intermediate defining our rate law. So when we rearrange, we say that the concentration of NoCl2, NoCl2 is equal to the KEQ, okay, the constant capital K EQ, it's a capital equilibrium constant, times the concentration of NO and Cl2. Now what we do is we say, oh, look, that's really handy, because now that's going to allow me to replace the concentration of NoCl2 in my rate reaction, right? My reaction rate expression, my rate law. So what I'm going to do now is step 3. I'm going to now substitute. Okay, NoCl2. So I can get rid of this intermediate in my rate law for my rate determining step, which is going to serve as my rate law for my overall reaction. So I'm going to say that the rate equals K prime. I'm going back to my original times, well, what is the concentration of NoCl2 equal to? Times, bring this down, KEQ, capital K, times the concentration of NO, times the concentration of Cl2, times the concentration of NO, right? Got to remember that I was originally multiplying by the concentration of NO. Simplify it, and I get that my rate equals K prime. And I'm going to assume that KEQ is quite negligible in this instance because, 1 second, let me write this out, is negligible. Because if I'm assuming that the other reaction steps are in equilibrium, for us, the constant that matters in determining the rate is the rate law constant specific to our RDS. The KEQ is a totally different concept here. So we're just going to consider it negligible for right now. Again, this will make a lot more sense when we get to unit 7. Okay. And I'll even make a note. Unit 7 will explain everything. Okay. So then we get that simplified that the rate for the RDS and thus the overall reaction is K prime times the concentration of NO squared, because we now have 2 NOs, one from our substitution and one from our original estimate of the rate law of the RDS, times, okay, the concentration of Cl2. And now what we have is a rate law that no longer involves the intermediate, but it does give us a pretty accurate estimate of what is the overall rate of the reaction based on the RDS. Okay. And there you have it. Oops, 1 second. And now we have an estimate of the overall reaction rate based on the RDS, but not including intermediates. Okay. So that's kind of the process of determining the rate law for a multi-step reaction when your rate law, when your rate determining step is not your first step. Again, all of this super complicated, okay, seemingly super complicated process here is only if your rate determining step is not your first reaction step. If it's your first reaction step, you can just stick it easy peasy, lemon squeezy. This is the dream right here, because then all you do is you just write the rate law for the entire reaction as if it's the rate law for your first elementary reaction. That's easy. That's why I'm spending no time on it. Okay, this is what gets complicated right here when your rate determining step is not your first reaction. So you have to assume equilibrium, and you have to get involved a concept that I haven't yet taught yet until unit 7. And you're just going to have to trust me that just know how to use the math. Okay, I will get to explaining the actual conceptual end of it all with KEQ in unit 7. So let's do a quick summary of valid reaction mechanisms. Okay, so a valid reaction mechanism, the elementary step. Come on, pen. The elementary steps. Oh, this pen is killing me. The elementary reaction steps sum. Okay, sum to the overall balanced reaction. Sum up to the overall balanced reaction. 2, each elementary step. Oh, this pen. Each elementary step okay, is unimolecular or bimolecular. You can technically have a term molecular, but it kind of defeats the whole purpose of, simplifying your reaction to increase the rate of probable successful collision. So like term molecular would kind of be like defeating the purpose. It happens every once in a while for like super weird, complicated reactions, very rarely. No. Okay, reaction, and then of course the reaction mechanism. aligns or confirms the rate law. And basically what I'm getting at too is RDS, right? Is your RDS matching the rate law that you wrote for the overall reaction? Basically what I'm saying. So, there is one more type of approximation that occurs. And this is when your first reaction is the RDS, but the second reactions or the third reactions following it are super close in rate 2. It's not enough of a significant change. So I'm just going to introduce this conceptually, and then I'm going to put it this way. For AP exam takers, I'll put it that way. For AP exam takers, you may want to watch a YouTube video that I have hyperlinked to the digital form, where it walks you through this process, because it's so similar to the other two in a way. It's like a mix of the two. And then I'm going to kind of leave it at that, because honestly, it's not a super common AP question. It was mentioned on the AP manual as like a subcategory thing that you should know about. I personally haven't seen a problem where you use steady state approximation yet in the practice questions and practice packets I've made. So I'm going to let you determine if this is worth your time. It is on the manual. It's not really clear the likelihood and how often and how in depth they want you to be tested on it. Okay. But I am going to introduce this, and people who are not taking the AP exam, you are welcome to continue watching for the next 5 to 6 minutes as I introduce some AP exam test takers content only, or you're welcome to log off. So let's go through a really brief overview conceptually, and then I'm going to leave the YouTube for you. Okay. You can choose to do this or not. Oh God, this pen. So for steady state approximation, when do you use this? Well, it's only used when your first step is the RDS, but the following reactions reaction steps show a very similar rate. Okay, they show a very similar rate. Okay. And so what happens is, what we have to do is we have to assume that there's a super low concentration of intermediate. Okay. Throughout the duration of the reaction. Okay. And kind of to represent that, the concentration of I is far, far, far less than a reaction involving A, B, and C. And so by doing that, what we assume is we have a steady state of intermediate concentration. And so how this works is that you have to select an intermediate in the reaction and calculate its low concentration, right? It's very low concentration. Assuming the above is true. And that's where I'm going to hand you off now to the YouTube video, because sometimes it's just better to have someone who's been teaching this a little longer explain it to you. And since it's, again, not super clear how well you need to know on the AP exam, I'm not going to stress about figuring it out myself either. I'm just going to leave it at this. I'm still new at AP. So sometimes there are going to be topics where I'm just like, YouTube can teach it better to you. Not gonna lie. So go ahead, if you are an AP exam taker, switch over to the 6-minute video, see what you kind of get from it. I believe it is a Khan Academy video. So some of you guys do love Khan. So he is coming in clutch for you. And the final thing I'm gonna say, you have a couple videos if you want a little bit more practice, is just comparing methods for estimating rate law. You want to remember that we can only determine a rate law experimentally. Okay. Reaction rate laws can only be determined experimentally. And so when we do all of this estimation, this RDS, it is truly an estimation. All of these RDS based rate law calculations are an estimation that would be confirmed experimentally. Okay. So, final thing for AP exam takers is just a little bit more on types of catalysis, because it is so significant in understanding reaction mechanisms. I'm just going to bust through this. And honestly, this is more, if anything, like a terminology kind of quick moment. So heterogeneous catalysts involve where your reaction is limited to a surface area. And usually involves a solid state chemical and or transition metals. A homogeneous type of catalysis involving a catalyst where your catalyst is the same phase as the reaction system. Same phase or state of matter. A binding catalyst, you mainly see it in biochem, right? But this is a type of catalyst where it actually binds to the reactants and assists with favorable positioning, favorable particle positioning. For example, see below, right? Enzymes are just your biological catalysts that do this. They're just your biological binding catalysts. For those of you interested in biochem, there's your like 1-second biochem lesson. And we call it like an activation site, like an active site where the enzyme and the protein, usually it's a protein, right, comes along, clamps in, and that allows another particle to come in, react with it in kind of like a grounded state, and thus more successful rate of reaction. So then we have temporary covalent catalysis, which involves actually bonding with the reactants. I'm creating an intermediate almost like an intermediate like product, but then the reactant the catalyst itself is still regenerated. Okay. And then finally is surface catalysis. This forms similar to kind of the one above. It forms a temporary covalent bond. Ooh, interesting how half my letters are not showing up. Forms a temporary covalent bond with the surface. So whatever material you're reacting on, with the surface it's reacting on. Okay, all of these, don't forget catalysis, a catalyst is regenerated, temporarily consumed, but regenerated. So all of these little types of catalysis, totally terminology thing. You just kind of want to know they exist. Okay, if you're given a question and it mentions something about hetero or homogeneous catalysis, it just gives you some background information. But the principle of catalysis, it holds true no matter what type. It is a chemical species, okay, that is added to increase the successful rate of reaction. And it is consumed, but always regenerated. So it ends up never being part of the actual overall reaction. Okay. So that's it. Good job, you guys.